primary members of the GCC, and has a really nice group that is built up with fantastic equipment. I've been there a few times to Institute, and really good piloting facilities when you're looking for the good mineral processing equipment to work with. Holger's group has fantastic stuff, and he's got really good industrial experience which he's taken back into academia, which I think we could do well thinking about in universities elsewhere. It's very strong in Germany, and I've realized that's such a good pathway. So Holger jumped in at the last minute to fill our empty seminar slot, so thank you very much, Holger. So let's see what he's learned about materials, which I find those little lines on the drawing board, they're the ones who give us the most problems. So I'm very interested to hear your view. Thanks, Holger.
Yeah, thanks for the kind introduction, Malcolm. Just to add, I have a background, very strong background in this materials handling side, because I've been working for 10 years with group, essentially developing materials handling systems there, in-pit crushing, materials handling, a bit of excavation, also in spreading. And then I was with Bäumer nowadays, having acquired in the meantime also FAM Magdeburg, also was in the business of materials handling and mining at Bäumer. Itself, of course, being quite strong in bucket elevators and pipe conveyors and even long-distance conveyors. So that's where they have perhaps the longest track record. And then I joined Tagraf, and Tagraf again, also being in long-distance conveying, pipe conveying. And so I took my old files and took some slides out, my old files. And I have to say, I am at the moment involved in a few not that funny issues with arbitration proceedings, and the materials handling always is a key in this. Whatever the other systems are, if it is in-pit crushing, if it is stockyard systems, but chutes design, elevators, conveyors, it's always an issue, and I will here and there refer to it. And so I thought it would be interesting to have a chance here to elaborate and to talk a little bit about these stump black lines in the flow sheets. To start with, essentially, we see, and that's my own experience, people have endless discussions about the core machines in the system, be it the excavators or be it in our case here, the processing plants, be it the crushers, the screens, the filters, the thickeners, the flotation, a lot of discussions, and everybody has to contribute a little bit to this. And in many cases, and I've seen this quite a few times, the question was, do we take a Sandvik or a Krupp crusher, ThyssenKrupp, or a Metso crusher? Then yeah, let's. The money is not there. Okay, let's take a bit of the money from the materials handling. That's cheap stuff anyway, and it makes up usually sometimes up to 50% of the overall investment. So it's good to cut down the costs on the materials handling to have a little bit more money on the nice machines, on the crushers and the screens, and the other machines. So apparently, the conveying systems are simple. Nobody expects any problems to come from that end. And this is usually a gross mistake. I found this nice slide in the internet from the bridge which collapsed recently. And I learned in a report that today, with modern bridges, it could not happen anymore. But with these old bridges, with these old designs, one link broken and the whole bridge collapses. So there's no redundancy in that system. And therefore, the bridge completely collapsed here. With one link collapsed, the whole bridge collapsed. And I thought it's not so different from what you find in many of our processing systems, in-pit crushing, conveying systems, in-plant systems. And even in my own laboratory here, I have a wet grinding circuit, complete one, with a new mill, and we wanted to do research on that new mill with a vertical roller mill with in wet grinding, and expectations were high. And at the end, we do a lot of investigations about the recirculation elevator. That's a chain elevator, and there is completely unexpected. I was not a friend of this solution, but what we found was really complete unexpected. And again, we had 2 years struggle with the system before we could really continue. So the dump black lines in the system, they often enough, they produce the problems because sometimes they are on the critical path. And if one of these links fail, think just about the line, the conveying system from the primary crusher to the processing plant. Quite often you have only one conveyor there. If that collapses, then the whole system is down. So the conveying lines, they deserve a bit more attention. Just think about how many single pieces, and the single pieces are at the end, the idlers, the belt is one piece, but the idlers, they might create problems. And the idlers, if one idler fails, it's not a big issue. But if you don't consider that one idler, and if he cuts the belt finally, and this happened a few times, then the system is down for one stupid damaged idler. So what we are going to talk about today, and I will introduce a little bit the various systems. I had to do a choice here because the time is of course limited, but I put in some of the conveying systems, and essentially I will be looking into the advantages, disadvantages, the problems which may occur, to just to make you aware that it's worthwhile to spend a little bit more time in selecting the appropriate system on that side. So we are going to talk about belt conveyors. Naturally, since belt conveyors are more often used than most of the other systems, so I will spend a little bit more time on the conveyors and the individual components of the conveyor, of the belt conveyors. But I will also talk about systems for vertical conveying, bucket elevators, talk about auger conveyors, vibrating conveyors, chain conveyors, various types. Many of you know the apron feeders. It's a type of an apron chain conveyor, essentially. I will talk a little bit about, very briefly, I will also touch on the fluid conveyors. Fluid conveyors, essentially, we have two types. We have the pneumatic and the hydraulic conveying. Particularly, if you look at the ore ducts, you have as many of the copper mines, you have ore ducts for transporting the ore, the concentrate, to the next port. So it's also worthwhile to think about these systems and to talk about briefly and the best application of these systems. And of course, I will end with a conclusion. So to start with, introduction, you see we are going to talk only about bulk conveying technologies. I'm not talking about any discontinuous materials handling systems. And for brake bulk, you have typically, every truck, every forklift truck is a materials handling device. Here we are only talking today about continuous conveyors for bulk materials. We can split those into the mechanical systems, into the fluid systems, which comprises the pneumatic and the hydraulic systems. And within the mechanical systems, you have a wide range of systems, and you find certain classification types. The one I used here is the one which differentiates between circulating means of tractions, like the belt conveyors, and without means of traction, like the vibrating conveyors or simply the chutes. I tell you, the chutes are among the most crazy things you can make the most mistakes in. So to start with, I have this general slide here, and I would like to start with the belt conveyors. I would then go into a little bit into the idlers and pulleys and devices. Let's see how the time fits. I would like to start with the belt conveyors. The belt conveyors, that is, there is something that doesn't work as I wanted it to work. I have to go back. We jump to some important slides here. This one, that's the one I was looking for. So the first point is we have so many conveying systems, different technologies. The question is where to apply which technology. And I tell you, there is most of the mistakes are made in selecting the wrong system for materials handling for certain material. So the materials characteristics is actually, that is the starting point. I can only recommend everybody to have a look into this one and closely analyze what is to be transported. And I have seen a number of cases, one of the slides I will show later, and up to very much recently, people tell me when the problem is there, then the operators say, hey, listen, you as an equipment supplier, you should have known that our material is always different from what we specify. How can we know what the material is going to be? And then if we do a blast and then the material rests somewhere on a pile before it is removed, then we have a torrential rainfall, then the humidity, the moisture increases, and then you have a lot of trouble with this. And this is something which is completely unpredictable. And so I have endless discussions of this type and hear it, and it's the end. No, it's not unpredictable. You know that you have in certain areas of the world, you have torrential rainfalls, or you have in certain areas, you have extreme droughts, and then the material can become extremely dusty. And so it's worthwhile really to look at the material, look at the particle size distribution. If you have huge lumps, you have to break the lumps before you put them on the belt. If you look, for instance, onto the lump here, you see that belt is overloaded, and you have a typical primary crush product. A bit further down, you see it's not overloaded anymore. So we see a question here already, a problem with continuous feeding to the belt. Can be a true problem. I don't know what is the reason here, or can be just that the crusher got a lot of fines at once. So there might be reasons for it. So, but this is definitely something you should not be surprised that you get spillage along your belt, which is finally a maintenance problem. You may have too large lumps on your belt, which is sometimes a problem of feeding the primary crusher. If you have a nice gyratory, which with the problems you have with the trucks, sometimes queuing up, sometimes no truck at all, so the crusher runs empty. Then you have low on the receiving bin, and then the crushing or the conveyor is stopped, the discharge conveyor. So, and then you have, if you have this regularly starting and stopping, I show you then a nice picture about a one-height conveyor for the discharge feeder there. So shape of the material is an issue. Then moisture. Is the material sticky? We had in a recent case gyratory crusher, and then the material the conveyor afterwards was completely flooded. It was like flooded with water because the material was clay, containing clay, and the clay, it looked like wet earth, but it looked like normal earth, essentially normal ground. But then in the crusher, it was compacted, the water came out, and then you had completely fluidized product. So moisture, stickiness, an issue. Stickiness, of course, impacts the crushing then, if you have a gyratory. Flowability in the chutes. If you have such a sticky material, then it's building up in the chutes, and you block your chutes. Then you might have segregation, you might have time consolidation in the chutes or in the bins afterwards. And of course, we have other issues like temperature, like fire or explosion hazards if you have certain material like sulfur or something. That is all, and there's many other characteristics you still should be aware before you think about even the best conveying system. And this is only about material characteristics. Then, of course, and this is something people are always aware of, then we have a certain transport distance. We have to bring the material from A to B. We have a certain lift on this distance. Usually, it's also known that we have a certain throughput to handle per time. So then we have ambient conditions, could be temperature, precipitation. If you're up in the Atacama Desert, it can be UV ray, which is dangerous for the rubber belts. And of course, and not the least point, is the costs involved in the differences. Varies. So you have to consider the capex on one side and the opex on the other side, particular energy and maintenance. And there might be even further selection criteria. This is just those which I consider most important, but I would not say this is conclusive. If you don't consider this, I just put here a few topics which popped up in the recent years with me. We have the block shoots. We have this thixotropic material here in a limestone quarry. Actually, there is certain corners with sticky material blocking the shoot. On the other side, we see that on this transfer terminal, these pictures, on the transfer terminal, that is, it was meant to handle fly ash. It was meant to handle fly ash, which is the gravity or the particle size of the fly ash is similar to cement because it's used to replace cement to a certain extent. If you look under the microscope onto the material, you see that the fly ash is almost consists of almost ideally spherical particles, very fine particles. And you look at the cement here. This is it looks like a zipper and it sticks like a zipper. So if you take a cement bag in your hand, you can grab it on the edges, and it is stiff. Usually, it's if you take it from the pallet in the do-it-yourself market, it's stiff like a board. If you take a cement which contains fly ash, it really it slides and it's really fluid. So it is worthwhile to think about it. And if you have this material, and in this case, that was even a so-called, we find later, a so-called processed fly ash. And with this processed fly ash, you might, there was a certain coarser part of the fly ash, which we were talking about 30 micron to 60 micron. That was separated and was used elsewhere. So we had an increased part of minus 20 micron, minus 30 micron fly ash. And then the question is, how do you deduct your transfer points? If you have a aspiration system, so back filters, if you have too much air, if you suck too much air, then all your fly ash will be in the filter, will end up in the filter. And if you don't do enough, then essentially it looks like on the picture here where we have a lot of dust. And this is something you have to be careful. This is the picture from the conveyor with this fluidized thixotropic material. And this is, imagine this is material after a primary gyratory crusher. And this is what comes out there. You can imagine the first slope that material would flow back, and you get into problems with this system. And of course, the arcing, I mean, that is, most probably everybody has seen this already. When all of a sudden you don't get material out of your hopper anymore, the apron feeder is still operating and the hopper is full, but no material comes out. This was a nice situation of arcing, which I photographed. So let's start with the belt conveyors now. Why do we do conveying at all? I mean, the point is, in many of the cases, we have to bring out the material out of a mine to the processing plant. If you are here in the primary crushing system, you see this nice picture from Escondida mine, and we see the crusher which is operating. You hardly recognize that crusher here. It stays here. That is the crushing plant where you have this, or similar crusher, not this one, installed. And then the question is, how do I get the material out of the mine, essentially? We are talking here about the biggest mine, potentially, or still the biggest mine in the world. how to bring out all the material from the different benches out of this mine. And this material is, most of the material is barren rock, so you just have to dump it outside and to bring it out to make enough space for the copper, which is in the center here. And it would be ideal if you could bring out the material straight out of the mine here, this straight green line. Unfortunately, there is no conveying system available at the moment which can do it with these masses. So you have to go the real system, and the real line is in this conveying systems, which is just there to bring out the material in a cheap way, cheaper than truck transport out of the mine. Unfortunately, that input crushing system is always in the wrong place. It's always hindering the materials. So we had a Stackcraft replaced or put it into different positions here in the mine, and finally it was taken out of the mine to the rim, because it's always interesting enough, always the biggest amount of copper underneath. So the slope angle for the belt conveying, for instance, it's still higher than the permissible slope angle, still higher than for trucks. So if you take the permissible angle, which is about 17 degrees, as indicated in the literature, which would be 30% slope, which is not or hardly negotiable with trucks. Therefore, you can go steeper. Whereas I have to say, with the 17 degrees, we had supplied one of these systems at 17 degrees with another Chilean mine, and the larger rocks already started tumbling back, and so it was prohibited to go along the conveyor systems left and right, because it could happen that some of the rocks started rolling back already, even at 17 degrees. Belt conveyors are interesting, of course, particularly for the longer transport. You see here this 9.6 kilometer system in Abra with horizontal curves and completely covered, so to prevent the UV rays to damage the belt. So for long distance, it's certainly a good system. That system has been in operation for close to 20 years with the same belt. That's also interesting, talking about longevity of these systems and the CapEx and OpEx. CapEx are comparably high, but OpEx were really amazing cheap. So it's about, I think, after 16 years, we started talking about replacing the belt. On the other side, you see a conveying system, which is quite often used in conferences as an example why the conveyors are really bad things. Because with the inclination of 17 degrees, and at the feeding point, you have to be shallower even. So you're not allowed to go too steep, and then to reach a certain height, you need to have a certain distance here. And if you see, you have your mills in Sierra Gorda, the mills left and right, and so you have to bring the material and to screen then and to bring the oversize back to the mills. And so you have a lot of conveyors here, belt conveyors, and the question, you have large footprint, and the question was certainly, isn't there a chance to have another system to make it better? I would have perhaps some ideas, but that depends again on throughput and material characteristics. So talking about belt conveyors, very briefly, everybody knows belt conveyors, I guess, just the main components we are talking about. Belt conveyors appear to be simple. We have the feeding chute, the belt, the idlers, the pulleys, the drives, the tensioning devices, the scrapers, and everything looks easy. The point is, if you look how many different components are there, just imagine how many components may get damaged. So we have to think about, first, what belt type do we use? What belt speed, belt troughing angle is to be used? The drive concept, what is the best drive concept? Belt tensioning for what is the conveyor dynamics? Think about it, such a 9.6 kilometer rubber belt, distance from feed to discharge. It's like a rubber belt. We saw with similar systems that when we start turning the head pulley, it took about 2 minutes until the belt and the tensioning device underneath the drive pulley really started moving. So you have to think about to about your tension pass, about how material you have to, how much belt you have to accommodate. What is the dynamics in the systems? There's dynamic waves oscillating along the belt conveyor when you don't do the right sorting concept. Then we have to talk pulley design, of course. You can make a lot of mistakes in the pulleys. I recently had a stockyard system. I had to investigate the stockyard systems where 76 pulleys failed. Wrong design, wrong manufacturer, bad luck. So most of the pulleys had to be replaced there. It was a design mistake. Don't use cheap pulleys. You might pay for it afterwards. So the right legging, what is the right legging on the pulley? Talking about idler selections, idler distance. Again, idler, everybody thinks idler is a simple thing. We have a steel cylinder and a shaft in and some bearings, and that's it. No, you can see nice surprises or bad surprises with idlers as well. So talking about idler stance, chain type, this belt cleaners, big issue. If you take cheap belt cleaners, you pay afterwards on maintenance directly, because you will see a lot of spillage underneath your belt. It piles up. At a certain point, it reaches your pulleys. I have seen drive systems being almost completely dunked in dust and spillage, and then you're surprised, or you should not be surprised, that the heat doesn't dissipate from the gearbox anymore, from the motor, if it is dumped with dust. So, I spoke already about chutes. So let's, I think for the belt conveyors, looking at the time, I will not go into all the details. We have to talk about fabric carcass belts, steel cord belt, talking about 9.6 kilometer belts. The difference, the major difference between the steel cord belt and the fabric carcass belt on the operation side is the tension pass. The steel cord belt has 0.2% elongation, while the fabric carcass belt has 2%. So that's 10 times more elongation, 10 times more tension pass. So 2% and 9.6 kilometers. You can imagine we are talking about 96 meters, 1%, so about almost 200 meter tension pass with a fabric carcass belt. Exclusive. So you can say no chance. Price-wise, not a big issue between the two things. And I put in this table here in particular because it gives you an idea. That is a selection table from the German DIN standard on the selecting of the thickness of the rubber cover on top on the selection. And you get an idea on the influences on this wear and on the belt, and what does impact the longevity on the belt. So you see, you have the loading conditions. If it is a short belt conveyor, then you have quite frequent loading. That is the second point here. Then the question, if you guide the material nicely on the belt, you accelerate already, you have a nice chute design, then you can accelerate the belt already in the direction. You would have less wear on the belt. But if you have sticky materials, these chutes, they would perfectly block them or jam. So there's also a question of operating these conveying systems, of course. Then the maximum particle size plays a role there. The bulk density, if you have heavy particles, specifically heavy particles, that could be easier damaging. Then we talk about abrasiveness. And abrasiveness, particular about, I would talk about sharp-edged materials. So we had an overburden in the Claremont coal mine in Australia. In some corners of that mine, we had sticky material, so the chutes were blocked. Then we made nice sliding devices. We removed the sliding devices, and then the original material, which is a basalt and very sharp-edged, actually it was breaking quite easily. It was much more competent than the original specified, but it was breaking nicely, but it was breaking with very sharp edges. And so when the chute was not guaranteeing the sliding anymore, it was really eating off the belt. It was chipping off rubber every time a larger block jumped into the belt. So abrasiveness is an issue, sharp edges, very important. And we have we can add this up, and then we can derive a certain number of millimeters for the surface. If you don't do it, your belt would look like this one. This is a belt feeder here, which is with the one which was started and stopped frequently. It had originally 32 millimeters of rubber covering the core rubber. So not even just the steel core. On top of the core rubber, we had 32 millimeters of rubber. And you can see that rubber was eaten off completely. And even, of course, then the belt is damaged quite quickly. And so it was repaired here, but this is not a long-lasting solution. So talking about idlers, exact positioning of the bearing, the rectangular positioning is absolutely important. Other than this, the bearings itself, and we had discussed quite frequently, even with German idler manufacturers, about the bearings where they were made, and they said, yeah, you know, we have FAG and SKF bearings, but whether they are made in China or Germany or elsewhere, the belt doesn't play a role anymore. The quality, as long as it is from the right supplier, it's okay. But the sealing, the knowledge is in the proper sealing here. If you don't have a good sealing and this type of labyrinth, you have multiple labyrinths here, as you can see, then your bearings are maybe quickly gone, irrespective of what manufacturers they offer. So the sealing is absolutely important, and don't go for any type of re-greasing. And also the bevel bearings, which were used some 20 years ago, I think they vanished in the meantime, hopefully. Another point, the rubber rings, the lower strand idlers look easy. You have just these idlers with the rubber rings to allow the spillage passing through. You don't have buildup on the idlers. Everything nice and shiny. I had an issue which caused 3 months of delay in the commissioning of the system. A 4 kilometers in-pit crushing and conveying systems. Idlers manufactured or bought by a well-reputed American brand. They manufactured it in China. Everything would look nice, even better than those here. So the surface was glossy, it was powder coated. The problem was with the rubber rings. The diameter, the inner diameter of the rubber rings matched exactly the diameters of these tubes. So when we started the system, it was completely, we started with the dry commissioning, switched on, the crushing plant was installed, and the spreader was installed, and in between 4 kilometers of belt conveyors. So we switched on, and after 4 hours, all the rubber rings, they were gone to the center or in one of the corners of the idlers because they were there's a press fit, and the press fit didn't work. Actually, when we had cut then the idlers and for preparation of our claim, we find that even water is in there in the bearings already after a short period of time that we had between erection and commissioning. So there was a few other things, but imagine for just this minor mistake, just the rubber rings having no press fit between the rubber to the cylinder here, and this nice and shiny glossy surface, the rubber rings gone, and you get into trouble and 3 months delay for the whole system. You see here those idlers in place, and even here, and this is taken, the picture was taken from a catalog of an idler supplier. Interesting enough, and when I look closer into this picture, I find that this belt is not centered anymore, and that corner essentially hits against these rubber rings, and so it's already programmed to get damage to the belt. So talking about idlers, I have to cut a little bit here the presentation. The running resistance of the idlers, and we are talking about the ceilings, we are talking about bearings. If you're talking about a short conveyor, 20 meters, 50 meters implant, no big issue. If you're talking about long distance, you see that the distance, or the difference between the running resistance, and you can see we have running resistance of 4 Newton here. That was tests which we did with idlers from various suppliers. We had 4 newtons here for the best ones, and we have 12 and even 17 newtons for another one as braking force at 0 degrees Celsius. So imagine you have 3 times the running resistance, or more than 3 times, 4 times the running resistance of the idlers. With a short belt, you have a lot of other resistances. That is this table here, it's by all the running resistances of idlers. For short belt, and I would just jump to the right columns here. We have a horizontal conveyor. We have 2 meters belt width. And the length of the belt is different. It's different, 20 meters, 150 and 500 meters, not really a long distance conveyor. But even here you can see for a 20-meter belt conveyor, the main resistances, which includes the idler running resistance and a few other resistances, it doesn't play a role here. Here we have acceleration resistance of the material in the chute friction. So these are the main resistances here. If you're going already at 500-meter conveyor, already this main resistance is already makes up for 77%. And then think about you have the wrong idlers and you have maybe 3-4 times that main resistance. And that not only plays into the energy, it gives you increased strength of the belt. The increased belt thickness means increased pulley thickness, means increased drives, means increasing everything. Like tiny little things about the idlers selection, the proper ones. One could then endless talk about the different diameters of the idlers. Of course, it may have merits if you go for larger diameters and the running resistance improves. So there are solutions with increased central idlers. There is a large molybdenum mine in the in United States that was built on a rail track, as you can see here, and the running resistance had to be extremely small. It's a 10 kilometers or no, 16 kilometers belt in one flight. And so the running resistance had to be very small. There would be used special measures to get this running resistance low. So talking about pulleys, I think I should skip this quickly. Don't use the welded design here, that's not lasting. Don't use stiffeners here in the pulleys. So you have to allow the pulley to flex. That is why we have this T-bone button or T-bottom. We have the chance to flex on the front end. Don't use this one. Of course, the legging is important. That the legging should be right. That was a picture I took in Thailand, in a limestone quarry in a cement plant. You see the legging was gone on that side of the pulley. Maybe a manufacturing mistake or what was, I could not find the reason out anymore. But you saw the belt was obviously already squeezed into the corner here. And so the belt damage would be the next. And the belt damage was then the real expensive stuff. So belt damage is important. Yeah, skip this one. Just go to the drive systems. Drive concepts, I think the drives, there is important that with the belts you run on the clean side of the belt. Don't use this triple drive with one pulley on the dirty side of the belt. There's a few things, or the most recent developments, maybe 10 years also in the market, is now the direct drive system, where you have essentially the rotor directly mounted to the extended shaft of the pulley, and you build essentially the starter around this pulley. That is nice, but it requires a different design of the pulleys. As you can see, you don't have the pulley shaft here anymore. You have a type of a cylindric element here in the bearing area to make the whole thing extremely stiff. Because why? Because you have to ensure that your air gap is minimum around here. And if you allow a flexion, the shaft flexing, then you have to have a larger air gap. And then the advantage which you wanted to have by direct drive to eliminate the losses of the gearbox, you get new losses in here with the larger air gap. There have been a lot of ideas about this splitting the drives. There is a nice system in the China conveyor in Australia where there's 2 tripper drives installed. The advantage there is if you see the stresses in the belt. The stresses in the belt, they drop at each drive, so you introduce new power into the drive, into the belt, and you don't need to have the full stresses at the end here. So you reduce essentially your belt stresses. You can go with a smaller belt, reduced idler diameters, reduced load because you have reduced load on the idlers. You have a lot of advantages, but essentially there's not too much really working systems. Time and again, you find ideas about this friction-based systems, the TT drive or belt and belt drive. Not really a good idea because you rely on friction factors and on the load of the belt on the top side of the belt. I skip the belt cleaners very quickly, maybe 1 point. I did a calculation, just 1.1 millimeter of dust on a 3.2 millimeter wide belt conveyor at 7 meters per second belt speed. That's what we have here in the Rhinish area in Germany, in the lignite mines. That is about 8 cubic meters per hour spillage. And now think about the maintenance costs if you have to clean it off. So belt tensioning, very interesting point, but no time. I would like to switch over belt shifting, but also just switch belt turnovers. If you want to avoid cleaning of the belt, you could think about belt turnover, but that's, as you can see, it's quite a huge structure here. That's again the molybdenum mine. So far we talked about draft conveyors. Now people might think about pipe conveyors. We come now to a few other conveyor systems. What is the difference between draft belt and pipe conveyor? First is for the same width of the belt, you can have a larger throughput with a draft belt. So that's very easy, very simple. Why do the people then use? And you have a lower running resistances because you can have at least in the lower strength large idler spacing. For the pipe conveyor, you have same idler spacing on top and bottom. But you have advantages with regard to the inclination. You can go steeper curves. You can go narrower horizontal curves. And so the pipe conveyors, and you have a complete enclosed transport of the material compared to the environment, or you protect the material from environmental impact like rain also. So therefore, pipe conveyors they made their way and they are quite widely used. And you can go up to 30 degrees slope angles with this system. The point is, you have of course to be very careful and very cautious with the maximum particle size in this. So that's about belt conveyors. We start some special designs here. We see these are more recent developments like this rope con, like this flying belt. You can download the lecture later on, and so you can read these explanations silently. And now we are coming to more to the lifting of the material. Talking about the lifting of material, I mean, I said it would be a dream for everybody to get the material out of the mine the shortest way at high capacities. Steep angle conveying, another slogan on that side from Der Sanders. So getting the material out the steepest and the shortest way, that would be ideal. Unfortunately, there is no means and they are capable in doing this. High capacity, steep angle, no chance. At the moment, there's no solutions. You find, for instance, the flexible belts, they can go up to 500 meters height. That's at least indicated by the supplier. They can go up to 4,500 cubic meters per hour. I have not seen this. This is again an indication by the manufacturer. Don't combine these both. You cannot go with 4,500 cubic meters at 500 meter lift. That's either or, very clearly. So 4,500, that maybe for 10 meters or something like this, not quite sure. And you see it's quite an expensive technical solution there with all these rollers in. Flexible is not good for large lumps. It's not good because they hammer on this cross walls here and these barriers and they damage it. It's not good for sticky material. You get the material in but not out anymore. So you have comparably high capex in OpEx. Still, these flexible belts, they are in operation. Just recently, there was a new one installed here in Germany, about 250 or 300 meters underground in the tungsten mine in Austria here. And they're also not good for deep temperatures because the material is vulcanizing material. It crystallizes at minus 20 degree, minus 25 degree, and then everything gets damaged. So if you want to get the cheapest, the cheapest way of getting material over a certain lift, over a certain distance, height difference, you are recommended to look for belt elevators. Or bucket, should be bucket elevators. So bucket elevators, we have two different systems, main systems. We have belt bucket elevators and chain bucket elevators, as you can see. The maximum lift for the belt bucket elevators nowadays stands at close to 180 meters height. And the throughput comes to close to 2,000 cubic meters. Again, either or, not the same thing together. The big advantage is with a bucket elevator, particularly with a belt bucket elevator, it's then cheap in operation. You have only two bearings which are permanently in operation. You don't have any idlers there. You just have the pulley on top, the pulley on bottom, a rubber belt in between, and the rubber belt is used to mount the buckets in. So similar is for a chain bucket elevator. You have the chain, two bearings on top, two bearings on top, and here you have the friction between the chain and the chain links. Again, you have to see what is the best, the most suitable approach. There is selection criteria here, and the point is, I think I should skip it. The bad thing, here you have the flowability. We didn't talk about flowability, but flowability is important for selecting also the means of transport. If you have material which is poorly flowing or is sticky, in other words, then you get it into the buckets, you don't get it out of the buckets anymore. Not good, like iron ore, for instance, the fine-grained iron concentrate. Don't use bucket elevators. I didn't include here the sandwich conveyors I found when I checked this. Sandwich conveyors would be the only thing where you can use sticky material, where you can transport sticky materials over a certain lift, because you can nicely clean it afterwards. Another means where you can go vertical, and you find it with ship unloaders, for instance, that is the vertical screw conveyor. As you can see, the principle is simple. It's completely different principles for example of slightly inclined screw conveyors and the vertical screw conveyors. Operating principle is different. And you have to be careful. Again, the material should not be too sticky. Otherwise, it doesn't work. The good thing is CapEx is rather low. Therefore, these things are used in ship unloaders quite often. You have just a pipe and you have your screw in, which is also mechanically easy to manufacture. But of course, large lumps are prohibited. Lumps which fit just in the gap between the screw and the pipe are prohibited, and cohesive materials are prohibited. And I just had a case very recently with a fertilizer material, maximum particle size 250 microns. And the coarser material, we had 5 different fertilizers here. The coarser materials flew easily, and we had no problems. With the finest material, majority below 100 microns. And when I looked under the microscope into the material, it was sharp-edged material, and it was the natural angle of repose was steeper than 50 degrees. And this material, it built up in the gap between the chute, between the pipe and the auger. And we got friction there. I tell you, the energy consumption was huge. And even with our system here in our laboratory, we have 11 meters system and very strong drive attached to it, stronger than common. The system finally switched off due to thermal overload. So vibrating conveyors. You find the vibrating conveyors very often in as discharge and hoppers in plants. I saw it also in a silicon plant, metallurgical plant, longer distance even. The point is, the vibrating conveyors are essentially quite easy to operate. You have an actuator. Say this is a typical one below a hopper. So the material is jumping over the chute. Interesting enough, you have very little wear because the material just hits. It should not slide over the chute bottom. It's just jumping and hitting and jumping and hitting. So the wear, the abrasion is very low. But and you get a very nice uniform flow rate, which is used for discharge. You can control it very nicely. It stops immediately once you switch off power. But the problem is if you have either very lightweight material in the recycling, in the fluffy material, it doesn't work. And I had it many years ago. We had supplied a stockyard system for iron ore concentrate in a port in the Middle East. And we had capacities there. We reached the capacities of, I think the nominal or the plant capacity was 1,200 cubic meter discharge. It's 1,200 tons per hour, the plant discharge. And actually we started with 600 tons per hour. And we were, of course, quite surprised. The client was quite unhappy about this discharge capacity. I was a young engineer. Very young at that time, and the reason was the wrong material, or better, not to the specs again. The material, the particle size was okay, was fine-grained, fine-grained copper concentrate. The problem, the moisture was too high, so specified moisture was 9%, up to 9%. And there we were at 12 to 14%. And you could take the material, you could throw it to the wall, and it would stick to the wall. And if you have this material and you have transport means which transports by means of vibration, so throwing the material up and then it hits the bottom again, it's thrown up again. If it is not thrown up because it is too adhesive, then you don't get a throughput anymore. So not a good idea then to use vibrating conveyors. So better to use scraper conveyors. Scraper conveyors, mechanical, they tear off the material. You find scraper conveyors in very different applications, like here on the portal scraper. You find this 3 scraper reclaimers here from Stockyard. That's a phosphate application in Northern Africa. You find a lot of scraper conveyors or drag chain conveyor, different name, in plant. You have a trough and you have your chain conveyor and it scrapes the material in front. Again, also these units, they are sensitive to sticky material. If you have sticky material, then it may not discharge, it sticks to the chain, it builds up to the chain. And the worst thing which we have seen is it builds up on the bottom, it sticks to the bottom, forming a stable layer, which it became thicker and thicker and thicker. And what happens if the layer becomes thicker, then your chain is stressed more and more, and at a certain point of time, the chain gave up, and there was chain breakage to the boat. You find, of course, the similar systems of chain conveyors in other applications. Here in the mines again, you have these feeder breakers. Usually the feeder breakers, they operate with these chain conveyors. You can use natural hoppers. Just take the dozer and doze the material onto the belt here. Onto the conveyor, and then it's being taken away. So you have, of course, and this is coming to an end here. That is, then we come to the apron feeders. That is from a nice washing plant, which we supplied to us. So the width of the apron conveyor was 3.6 meters. We had already some damage, as you can see here. Some of the bars were already broken. The width was 3.6 meters here. The lumps were specified with maximum 2 meters. You can see these lumps just fitted in between, and so we got some damage. All these stiffeners, these bracing bars which we had put on top, they were taken away. This is the most impressive movie seen. You see this height limiting device. We had a height limiting device on this after the hopper, because the smart idea was to prevent this. We have this breaker, this bar on top, and it's quite robust. That's it. The bar was gone. You see the crack here? It's like a match. You cannot withstand these forces there. Continue. Next slide. So, few words on fluid conveyors. Time is almost gone. We have the fluid conveyors. There's a wide variety actually of these fluid conveyors, particularly talking about pneumatic and hydraulic conveyors. We are talking about pipe and trough, which means closed and open. And in the trough, we talk about pipe material and particulate or lump material. And you find for each combination here, you find actually in the industry or found applications. So for instance, for pneumatic conveying open trough, you have the air slides, which is used in cement industry occasionally. You fluidize the cement and you can have it running like water on very shallow slopes. You have the hydraulic transport in pipes, very nicely running on the ore ducts. So simple design, low capex, you can have a very narrow, rather narrow curves, of course. And then if the narrow curves are there, then you have air there, and then your OPEX are increasing. So the fluid conveyors in the pneumatic conveyors, which I have seen quite often in the cement industry to transport the ground cement, they were gradually replaced by the pipe conveyors there. While in the pneumatic conveying, you still have the ore ducts, and sometimes it's even in combination with technological purposes. So if you go to the oil sands in Canada, you see that the hydraulic conveying is even used already with special water, hot water, to separate already the oil sand or the oil from the sand in a first preparation step. So hydraulic transport, you can see low capex, long distance possible. You see, by the way, even if you have the tailing ponds, you can nicely see in the tailing ponds a laminar flow of material. Material is transported into the tailing ponds and then distributed there layer by layer. We had interesting investigations we had done on removing tailings in Chile. There are some legislative measures to remove the oil tailings in certain altitudes, and we investigated the recovery of these tailings because there were really some high-grade horizons in these tailings. So most important point there to see that you don't get too much sedimentation. So particle size plays a role there. So particles should be quite fine, and density plays a role, and you have to find the right fluid velocity to get the material really to prevent sedimentation in long distances. So maximum flow rates, let's skip this one. Conclusion. The dumb black lines in the flow sheets, I think they deserve more attention in the future. So there's a wide range, and I really rushed through the range of conveying principles which are available. Even the sandwich conveying, I didn't talk too much. I didn't talk about cable belts here, and there's a few other means which I skipped. Then the selection, it's important to select the right means of conveying. What is the material property? That is a driving decision is a material property, of course, send the throughput and then the transport path with the lift and everything. And then, of course, also the costs to be considered. And of course, a careful selection is important to assure that we have a high system availability. And we want to make money out of these systems. We are talking about producing the concentrate here in this case and shipping it to the port in the cheapest possible way. And the very simple and the very basic point is that we achieve a high availability of that system, and not only of the SAG mill and of the ball mill and of the flotation of the crushers, the whole system. And if you count the number of black lines in that system, and this is just a very simplified system, you find that there is a lot of, it's very important to have a closer look into the conveying systems, even if we are essentially usually talking in these lectures here about minerals processing. That's about it. Thank you very much. Thank you for your attention. And if you have further questions, you have my contact data here. And I'm glad to answer questions now.
You
Thanks,
Holger, for
Holger.
the very interesting presentation.
Very good. I know you've run to full time, but those who want to stay back and ask some questions, you're most welcome to. Really a practical and informative seminar, I might say.
I'll go for one, Malcolm. Hi, Holger. This is Shujat here.
Hi, Shujat.
Great talk. Really enjoyed it. I see this happening quite a lot where I work currently. What's your take on belt drifting, by the way?
Yeah, belt drifting is quite a big issue in many applications. And the first thing is for belt drifting essentially is to ensure that you have a proper feeding to the belt. That is easy said, but the chutes already react differently if you have 100% throughput or maybe 20% throughput. If you have 20%, the material might dribble out of the chute on one side of the belt, and then if you have a fully load, then with the same chute, the belt is more shifted or the material is shifted to the other side. On the draft belt, so essentially you have a balance of forces, and depending on the center of gravity. If you feed the material on one side of the belt, and the center of gravity is sitting on one of the wing idlers or the wing idlers, and then it shifts the belt to one side. So that might be at one point. In many cases, it is a reason. Then you have clocking material to the pulleys. We have seen even snow sometimes. We have seen snow, even larger damage, where the people cleaned up the belt and they didn't recognize that they had pushed the snow on the lower strand that traveled to the tail pulley. There was a scraper, the blow scraper, but obviously the pile of snow, it jumped over the throw, or part of it jumped over the snow scraper, was clamped between the pulley and the belt, and then the belt drifted away. Now talking about means of correction, very small, very little chances. The most common one and the most effective one is the banking of the wing idlers. So you put the wing idlers, you incline in the transport direction slightly 1-2 degrees. That you essentially, when the belt drifts in one direction, you get more load on the wing idlers, and these wing idlers would move the belt backwards and the other side. Disadvantage, as usually, you have always disadvantages with these things. You increase the friction, or you have a permanent slide of your rubber on the idlers, so you increase a little bit the friction, the wear, but particularly the energy. You have to calculate the energy losses. There is then a lot of patented solution on systems where you have these swinging systems. Some crazy people even try to put vertical rollers or vertical idlers on the edges to prevent the belt from lifting off. If that happens, the belt runs against these idlers. If the forces are small, then they might prevent the belt jumping off. But in many cases, they lead to damage of the belt edges, or the belt then first it folds and then it jumps over this, and then it scrapes on the shafts of these vertical idlers, and then you get really damage. So I think, and all these moving things which have a pin in the center and then they start swinging. My experience is after 2 years, that is blocked in a certain end position, and then it permanently tracks the belt in one direction, irrespective where the belt really should be shifted to.
All right, thank you.
Thanks.
Any other questions out there?
I will ask a question, Holger.
Yeah. All right.
Thank you very much for a very, very good presentation. Many people, when they are looking at the conveyor belt design, they are mostly concerned with power and tension and so forth. But we've seen a recent trend where people are having very long belts.
Yeah.
What is the impact of having these long belts in terms of servicing it properly, as well as the life of the actual belt?
Yeah, usually one can say the longer the belt is, the longer usually also the lifetime of the belt is, because the most wear on the belt, on the carrying side of the belt, occurs during acceleration of the material and the feeding area. So now think about, you have a long distance belt conveyor with say 9,000 meters one distance, and you have a transport a velocity of, make it easy, 10 meters per second. We are not running at 10 meters, but maybe 7 meters or something. So, but let's assume 10 meters, then we have 90 seconds in 900 seconds in one direction and 900 seconds in the other direction. So that is 1,800 seconds, which is half an hour. So you load the belt only every 30 minutes. And so now you can count on how often this happens in 10 years. Now think about, you have a short belt, 20-meter belt. They are not running that fast, and let's say 4 meters, and let's say an 8-meter long belt. So that belt is loaded every 4 seconds. So that is that tells you how often this occurs. And we have this mobile conveyor bridges here in the German lignite mines. They run at that time at 11 meters per second. To have the special or the load per meter very little, and to reduce steel structure work. And so initially the idea was, to have an acceleration belt, so-called acceleration belt. That acceleration belt was about 40, 50 meters long to accelerate the material, and it was meant to concentrate the wear on this belt and to replace it more often. And so these acceleration belts finally were removed, because it was found that the downtime of the system was, with this acceleration time, much higher than without these acceleration belts. So the original belt was slightly extended, so the acceleration belt was removed. Normally these bridges, they have a length, total of the maximum length is about 700 meters here to bridge the mine. I think the longest single belt is 400 meters. And nowadays, none of these bridges has this acceleration belt. And we had a similar case in Freeport, Indonesia, we had a spreader there also with an acceleration belt, same thing. The acceleration belt wore out very quickly. We then went from the original supplier to another one, so at least we came then to 6 months lifetime of that belt. Again, it was running at close to 10 meter on this spreader, because we also wanted to, or the client wanted to have a long boom spreader there, and so there were some restrictions, but we had an issue there. The original belt that was worn out in 2 months or something like this, so too often for practical operation.
Thank you, Holger.
Yeah, any other questions?
Yeah, I got another one. Shujat again here.
Yeah.
How can we control? Is there a way basically that you recommend to control segregation on the belt?
Actually, you cannot control segregation itself on the belt. Segregation, or what I would call segregation, is that essentially you have the finer material is essentially first, the finer material stays in the center. If you have coarser lumps, they roll to the side, and you can see essentially on the conveyors that after the material is loaded on the belt, very often you can see that there is in the center your finer material and the coarser lumps are the sides. During transport, then on the longer side of the longer runs of the belt, you get then the segregation that the finer particles you have passed through the coarser lumps in the bottom, and so you get at the end of a long distance conveyor, you see only coarser lumps because the finer material then made it to the bottom, and the density of finer material is higher than the density of the coarser lumps. We use it, by the way, for the pelletizing tables, for the iron ore pelletizing. There are the coarser pellets. They float always float on the top, and then they jump over. We use this system. You see the same thing on the belt conveyor, because you have essentially on each idler, you have a certain motion in the material. When the belt is passing an idler stand, you have a slight motion in the material, and this is enough that the finer particles can pass through. This is about the vertical segregation of the particles passing through. I think you are looking forward to the swaying of the belt, the shifting of the belt. The only chance there is that you have a proper chute, which allows that the material is already perfectly, or desirably, it should be accelerated into the length of the or along in the direction, the transport direction. That is also good with regard to the wear. And essentially, that would also allow, if you go in the same direction as a belt, that would allow that always the material is centered. Unfortunately, in many practical cases, it's very difficult to reach this. You need more height then for this type of chutes than to direct the material appropriately, which is costs again energy for lifting the material, and there's other disadvantages. So somehow you have to find the compromise. Hope this answers your question.
Sure. Yeah. Thank you.
Yeah.
Right. Thanks, Holger. I've sent my private question direct to you.
Okay.
There's a question waiting for you when you get off here. Thank you very much. Really appreciate you contributing. As Marcelo said, you've got enough material for an academia lecture here, so we might rope you in next year to pull a full lecture on it. Really good. Thanks everyone for attending. And young Shuja is the next presenter next month. So he's been active this one, asking questions.
Yeah. Thank you very much, and have a good time.
Thank you, Holger. Thank you, everyone.
Holger.
Thank you, Holger.
Thanks,
Everybody
Holger.
say
Thanks, everyone.
bye.
Oh, great.